This video is about some Hungarian results about quantum communication. But let's start at the beginning. Quantum. I suppose you've heard the word quantum regardless that you live in Hungary or not. You might have heard it in the context of quantum computing or quantum communication. In high school, you have learned about the famous physicist Niels Bohr. He said, "Anyone who is not shocked by quantum theory has not understood it." If you do not understand the basics of quantum computing yet, you should watch some other videos before this. If you are familiar with the essentials of the quantum computing, let's continue. Quick check with the very basics. Did you know that a quantum bit can be not only in two states like the classical bits, but quantum bits can be in the superposition of 0 and 1 at the same time? If you know this and some other information, you will understand the last. Probably you've heard that the widely used RSA encryption algorithm can be cracked using a quantum computer. So your credit card credentials and all work emails could get public. Although the quantum computers today are not large enough to break RSA, but it is a security risk for sure. The quantum world brings not only threats, but also new opportunities to security solutions. One of these is quantum key distribution, or shortly QKD. What does it mean? There is an algorithm to break asymmetric encryptions like RSA using a quantum computer. But symmetric encryptions are still safe. The word symmetric means here that the sender and the receiver have the same key, so their communications can be private. But how to have the same key at the sender and at the receiver? That's what quantum key distribution is for. I cannot cover the whole algorithm in this video, only the basics. Why is sending through a quantum channel safer than through a classical channel? Let's see the overview of the QKD between Alice and Bob. Alice transforms the classical bits into quantum bits, then sends them through a quantum channel to Bob. Bob measures the quantum bits, so he'll get the classical bits. What if there is Eve who wants to get the message in the quantum channel? Eavesdropping is not an option because of the no-cloning theorem, which means that quantum bits cannot be copied. So only active interception can be done by measuring the quantum message. But a measurement modifies the state of the quantum bits, so the measurement can be detected. If you detect the measurement, Alice must send a new key. So you can transfer a key safely between the sender and the receiver. In Hungary, the quantum key distribution has developed a lot in the last years. In May 2022, the researchers of the Budapest University of Technology and Economics set a national record using QKD, to be more precise, using continuous variable quantum key distribution. They used self-developed hardware and software. The distance between the two stations was more than 20 kilometers. This was an experiment, but it might be a part of a future quantum communication network in Budapest, capital of Hungary.